Okay. Would you like to start? Everything's ready.
Sure.
Okay. So I hope everyone is coming from the break. So we'll start with the next session. Okay. Thank you everyone for joining for this one. So in this talk we have David Morcuende. David Morcuende holds the position of new technologies expert at Mahou San Miguel, which is a company in Spain that specializes in beer and other beverages. And he leads the data science, AI, IoT collaborative platforms, Web3, and Technology Observatory, specifically for quantum computing also, those knowledge centers. And apart from that, he's a Qiskit advocate and an active contributor to Qiskit. He has completed several projects on that, and he's also the organizer of meetup that we have here in Madrid, which is Quantum Madrid. And among other projects, he has also worked at Telefonica in the BBVA AI factory. He also launched a startup and directed the research and development department of another one. So thank you so much, David, for being here today and agreeing to deliver a talk. All yours. Thank you.
Thank you. That sounds amazing. So first of all, in this talk, a big disclaimer. I'm not a physicist. I'm an engineer, so I'm used to like build and break things, not so much in like thinking on development new ways of thinking or algorithms. So with that said, let's go. I'm David Morcuende. I work at Mahou San Miguel. I I have knowledge of a lot of these technologies. I'm also a Qiskit advocate, as Rafa said. And if you like to be one or just are curious about what the advocates do, just go to that website, qiskit.org/advocates. So what I'm gonna talk about, mainly about projects I have done or I have been involved. But the first, I don't know if half or less than a half, I will talk about how circuit works, because I think that is a topic that is not so much covered in many places. And when people talk about quantum computer, they think that everything is a circuit or something like that, and everything works just like that, and that's not. So I'm gonna cover that. Then we will see two quantum computing SDKs, Qiskit and a little bit of the Braket SDK. I will focus on how AWS Braket service work. I'm going to explain the devices they have and the integration that I did with other partners of IBM, building a provider from Qiskit to Braket. This means that you can write Qiskit code and execute in the Braket platform. We will see another way of representing states, quantum states. It's a project that I really like that is related to quantum art. And at the end, I will cover something about the phase estimation with the phase estimation algorithm and the EPE, like the iterative phase estimation algorithm, and how things are evolving from the like normal usual quantum computing to the hybrid quantum classical computing. So let's go. How circuits work. So I have here a matrix that explains pretty well that what's the purist says about what is a quantum circuit and and what the rebels can say. So in the more pure concept is like a Boolean function that is a circuit like the classical functions. And in the top, you can see like in the purest thing is like there is a classical circuit. This classical circuit can convert to gates, and those gates are pulses. In the real time, everything is about sampling, like having algorithms like the IPE that I'm gonna briefly cover at the end, and again pulses. And if you are a rebel, everything can be a quantum circuit, and everything is quantum. So the transpilation process. the main thing and the thing that enables us to work with quantum processors and these quantum computing algorithms is the transpiler, because you are used to work with circuits, and these circuits are transpiled to another circuit that can be executed in real quantum devices. In that process, there are a lot of passes like the virtual optimizations, the like translating the actual gates to gates that can be executed, because Hadamard gates are not Hadamard gates when you execute them. So we will cover everything. So why we need to transpile circuits? Because circuits are abstract and device agnostic. That said, here I have bring you, I think it's the Nairobi circuit by IBM, and we can see like the couple mapping that for example, the first qubit or the zero qubit is not connected neither with the second or the third qubit. So we have to have that in mind in order to execute real gates or real algorithms. Devices have constraints, for example, calibration or connectivity. On the right, we can see like the Nairobi circuit has some error in the second qubit, and we can measure that error, and let's, if we want to execute something in this circuit, in this hardware, we have to have in mind that if we can avoid to execute things with the second with the second qubit, like the second layer of the circuit, we should avoid it, and the coherence and all this stuff. So what's the benefits? So hardware development is going so fast. I have been in like the last IBM conference about their new Eagle processor. I think it is that it has nearly 500 qubits. So it's growing so fast, and the software isn't growing so fast. So transpiling gives us the possibility to execute our old software in the new hardware. In Qiskit, every time you execute something, it is called into a transpile function after executed. And it's a super great area to start in the quantum world, in the quantum developer, because there are a lot of open problems, and there is an active area of research. If you don't believe me, from the 774 open issues in Qiskit-Terra, that is where the transpile is, there are 35 open that has the tag good first issue. So it could be a good way to start to develop in open source and learn something about that. It's usually easy because it's so intuitive. It's like mapping things. So it could be a great chance. So let's go with the abstract quantum circuits. We are talking about that there is some gates and in the circuits that are used to execute things. But in reality, those gates that you are using aren't suitable for the hardware. So I have bring here an example of what does a circuit look like and what is the transpiled version. Here we can see like that the Hadamard have been converted in some rotations, and the controls have been changes. So that allows us portable programs, and it requires some processing, because to couple everything, you need to know what is the real mapping in the hardware. And how can we do that? Everything is coded in the Qiskit framework. So if you have any problem or you don't follow something, just write in the chat and we will try to solve it. So this is a quantum circuit that has a Hadamard to control X and a measurement. And this could look like a well-formed circuit, because if I execute that in the, for example, the QSM simulator, it will run successfully and it will give us a good result. But in the real world, when we are not using simulators, we are using real devices. For example, the Nairobi hardware that I have shown you before, when you try to compile, assemble, and execute it, it throws an error, like the object includes an instruction that assumes a coupling map. I don't know if I have, yeah, I have here like the slide. We are trying to execute this circuit that needs that the first qubit and the second qubit needs a connection with this CNOT gate. But in reality, we don't have that. So we will have to transpile. And this gives us two good advantages: the compatibility and the optimization. Because transform a given circuit into one which is executable gives us all the compatibility, and we will see an example of different architectures, for example, superconducting and ion traps. And the optimization, because if we have to mesh to map the gates to another gates, we can make that coupling or that translation better, minimizing the influence of the coherence, the errors, and trying to avoid those qubits that have high error rates. In the compatibility area, you can have more instructions. You can have you can translate the basis gate to a native gates. With the initial layout, you can say, if you know where are your errors, try to move that qubits, and we will see an example of how you can change the initial layout and optimize the circuit. Making the coupling map and the device architecture. So let's start with the optimization. You can reduce the logical gates between your circuits. So for example, if you have two nodes that one follows the other, it will cancel. You can actually execute that, and you can have those instructions at the same time, but it will cancel. So with the transpilation, the circuit gets better, so you don't have to execute two gates that will increase the coherence. It can compact single qubit gates that we have seen, and the cancellation. Another way of optimize this is with device-specific reductions. So if you are aware that this is, I think, a Lima hardware, if you know that, for example, this hardware has the second, the third, and the fourth qubit that has more error than the other qubits, you should be aware of that and try to change or your circuit or your hardware. And I have bring here a picture, like the right most bottom picture is the directed acyclic graph that is working behind all your circuits. When you are trying to run something, it will build something like that. And I will talk about a project that I was involved that has this. So in Qiskit, for example, you can have up to 4 levels of optimization when you are transpiling your circuit. You have the very first level, that is the 0 level, that just maps the circuit to the backend. This is a one-to-one mapping, that is an identity that it says, well, we have the backend, either a simulator or an actual real quantum processor, and I have to execute this circuit. So transform all the gates to actual rotation in the superconducting case, for example, and execute it. This is good what you are testing, like new algorithms or something that you don't really know how will be affected. You can use that. With the first level of optimization is for collapsing adjacent gates. As we have just seen, if you have two nodes together, it will collapse the two nodes. Or if you have some rotations that can be translated to one rotation, it will collapse to only one rotation. In the level 2 of optimization, it's like a medium weight optimization. It will take longer. If you are working with toy examples or some small examples, you didn't even notice. You don't even notice the time consuming. But if you are working with big algorithms, you will start to notice that the execution will take more time, because this is like optimizing all the circuit. With the level 3, it will like rethink all that have you done, and it will like try to make it as good as possible with the circuit that you have provided. There are some things that you have to have in mind, that the higher the optimization level, the higher the fidelity, the lower the depth at the cost of longer transpilation, longer time. But there is a problem with the transpilation thing, and the process is that this process is hard. In fact, it's super hard. It's an NP-hard problem. So it's if you will try to map this with brute force, you will probably never find the real solution of that. In Qiskit and in many transpilation processes, they try to find the best and the optimal solution, but it uses heuristic algorithms, so it may not find the optimal swap. If you are testing, if you have some problems, if you want to know what your circuit is really doing, you can have barrier operator. That is a pipe that you can set in some parts of the circuit, and it will prevent the optimization. So as I have said, in Qiskit, everything is transpiled before being executed. So if you don't want something to be specifically transpiled, for example, two gates that may be together that they are canceling or something like that, you should use a barrier, and it will not optimize. But let's go with some examples. So imagine that we have this circuit that we are transpiling it with something that is called the basis gates, that you are forcing it to only use U rotation or control nodes. And with the transpile circuit, we can see that everything goes fine, because if you are not saying the algorithms that any mapping, as we have said with other hardware, it will try to find like the best and the optimal solution. But here we are saying that we have the Jakarta backend, that is a fake fake device, and we are trying to optimize it. So it will try to look for the best solution, knowing that there are some errors, and the gates, the qubits may have a low fidelity rates. So this is the example without saying any optimization. It has like 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 10 CNOT gates, and we optimization with the level 3. It has reduced all the CNOTs to 2, 4, 5, 6, 7. So we are saving 3 CNOT gates. That it may not look so much, but believe me, when you are working with real devices, it's a lot. even if you know that, for example, in the other devices that we have seen, we know that, for example, the second qubit or the third qubit isn't working properly or have high error rates. You can use the initial layout that is here. The initial layout argument says that you are changing the first qubit for in this example, the sixth qubit, and the second one with the third one, and the third one with the fifth one. That is done, as I have said, if you know the device and you know the error rates and you don't want it to optimize in that level. So let's see some example. For example, the Bernstein-Wasserstein circuit that is a solver for such problem. So here we can we want to execute it in a superconducting qubit devices and in ion trap devices. For those who don't know, this operator is the barrier operator that I have said. So everything before this is transpiled, and everything after this is transpiled in another way. So using only the U3, the rotation in the U3 and the control node, we can execute this same circuit in almost any superconducting qubit circuit device, and only using rotation in X and in Y's, you can execute it in ion trap devices. For example, if you want to execute this in ion Q devices, the first circuit, you have to use this one. If you don't use this one, you will get an error that the device doesn't have the appropriate gates. So we have talked about the transpiler, and I want to just bore you a little bit more with the directed acyclic graphs. That is the task scheduler and the part of the Qiskit compiler. And it's a project that I really like because I was involved with. So imagine that you are building Qiskit, that is a framework to work with circuits and executing real devices, and you need something that is super fast, that can calculate all the possible directions and nodes to transform the circuit, the pretty circuit that we can see like here. All these pretty circuits has to be transformed in something that the machines can understand and that flow with a pipe. So so they develop Rustwort, that is a library written in Rust with compatibility with Python, that make all these things. This is the first link that I'm opening. So here is the actual documentation, and I was involved in written one of the functions of this library. And as you can say, this is what is behind all the processes when you are running a real circuit. This is the one that I made. That is one of the generators. That is the full Rari tree. If you want to know more about Grassworks or the generators or graph theory, don't hesitate to contact me in LinkedIn, by mail, or something like that, because I think it's a really cool thing, and it's part of the new quantum era. Okay, let's go with the cool things. We know and we have learned how does these circuits works in behind, but we want to work with SDKs. We want to leave the Qiskit world with superconducting qubits, and we want to execute in ion traps and, I don't know, diamonds, any other technology that you want to know. So we can go to Braket. Braket is a managed quantum computing service. It's a pay-for-use system that today have the Wave, IonQ, Rigetti, and many others. and it makes the access to all of these systems easier, because you have a single framework that is called the Braket SDK that you can use. You can work you can develop in the Braket SDK, and below it will transpile to the actual system that you need. So let's see what are the capabilities of Amazon Braket. So right now we can use all the devices that are owned by AWS, that are simulators. Those three are simulators. Now the IonQ device is available, but the Oxford Quantum Circuit in this time zone is not available. We need to wait 15 hours to get an execution here. We have the QERA that I think that the AWS people have told you about. One of the Rigetti devices are offline, and the other isn't available for the next 9 hours, and Xanadu are offline. So great, we know that we can execute in all of these systems. But how do I build a system that can talk with this Braket SDK? So last year we started a project with IBM that it was to build this provider that Rafa told you about, and maybe the AWS guys told you. And you need to know something about Docker, the hybrid jobs that I think that they are super awesome, and I will explain you in a moment an example. Make the actual plugin and make that Qiskit works with Braket. So you need here in the Qiskit layer, we have providers, backend, and jobs, and we have local or Braket. This is connected to or the local devices or the AWS devices that we have just seen in their web, and those devices are executed in tasks, not in jobs, as we said. And an example of that is you define in Python a Braket provider. In the backends, you say that the name is Rigetti, and from the Rigetti devices, the one that the status is online, and just running and get the comms. So let's see how does this work. I have explained something about that. So here we can import the AWS Quantum Jobs, the provider, and the local backend. I think that should be better for you. From the provider, we get the backends, and by the time that we execute this, these were the devices that were available. And here we can just select the SV1, for example, is a simulator, and the IonQ, the Aspen M1, is an actual real device that is by IonQ, and I think that is an ion trap devices. And just you can work as is. Everything will run perfectly, and you will get high error rates. But anyway, I want to tell you a thing that is even better. That is that you can use the libraries and all the algorithms that Qiskit already have. For example, the VQE. You have an implementation of the VQE in the Qiskit algorithms module. So with this provider, that is a really good thing. You can just get the backend that you want. In this case, it was a simulator. Define everything that you need. Import the VQE module and just use it. And you don't have to like wait for the IBM queues or something like that. If you have the AWS and it's some of the devices are available, you can just run it in AWS. The good thing is that you can use a lot of different devices The bad thing is that you will have to pay because AWS is a paid service. So having that in mind, I want to talk about the hybrid jobs. Hybrid jobs, I think that is the way that quantum computing is going, and it is the thing that you need to build actual algorithms that have some impact in our day-to-day or in our jobs, because we need either classical computation or classical data and run it into quantum computing devices. Amazon has an idea and a service for that is called the hybrid jobs. So the user can execute with the Amazon Braket IDs or the console the hybrid jobs, and everything that these jobs execute will be saved in S3 as a result, and in CloudWatch as the terminal output. So the CloudWatch that we will see, it's like if you open a terminal, write some code, and the output is
Sorry to interrupt. David, can you hear us?
I cannot hear.
Yeah, something is, and I think it's not able to hear us either. So, okay, give me a second. David? No, I think he's on full screen. So, David, can you hear us?
Maybe Rafa, you can stop sharing his screen and he will realize that something is going on.
No, I think he already realized.
Okay, that's good.
I don't know if you hear us. So basically, the audio is not working at this point.
okay. Can you hear me?
No, it's working now. Okay, it's not being allowed. I think it's like 3 minutes, 5 minutes at most. It's not that much.
Oh, where I where I mute myself.
That's fine. So maybe, yeah, I think we were here. So the last thing I heard was, I think it was about CloudWatch and the integration, but I think we lost you at some point.
So it's okay. The CloudWatch service is like if you were executing your own code in a terminal. So everything that will output in your terminal, it will be written in CloudWatch. We will see an example that is super clear with that. Here I was saying that I have copy paste the bracket documentation, and it says that it's for convenience mainly, because you have out of the box all the algorithms and all the things that you want to execute. The metrics thing that is that, as I have said, the CloudWatch and the S3, because all the outputs will be saved in an S3 bucket that is like a file storage. And the best thing and the thing I love the most about hybrid jobs is the performance, because Amazon says that you have a priority queue in executing in real devices when you are using hybrid jobs. And I was opening this example that I was saying that the good thing that is super easy to use and to execute is that you have to only prepare your algorithm. You can execute it. This is a quantum machine learning model. You have to have a custom container that is a Docker container. If you don't know about Docker, it's a virtualization thing that enables you to execute all things in a virtualized environment, and you don't have to use a real computer. And create that Docker in the ECR, that is the Elastic Container Registry, that is a service managed by AWS, by Amazon, and it has a cost, it's super low, but you have to have that in mind. And then you only have to execute that in the AWS environment. And I was just showing you how to execute a hybrid job using Qiskit. So we will use an algorithm that is already in the Qiskit algorithm part. So here we have defined the script, the .py script in Python. Our Docker image that we are using a Ubuntu base for bracket. We have, as I have said, you have to use the Elastic Container Registry in AWS, create the repo, build the image, and just run the job. And that's it. You are running in a, in a cloud, a device that is, I don't know, everywhere. So how does it looks like in a real execution? So this is the Elastic Container Registry that I have set. I have seen here several. We can maybe jump into one. This has no images. So this is the Ubuntu I have set. We have all the information here. And I want you to see the bracket service. Here we have a lot of information like the recent jobs, some info. Here in the panel we have like the main panel, that is the main panel, the devices that we have just seen, notebooks. If you have any notebooks, you can you don't need to have anything installed in your PC. You can just create a notebook and use it. Remember, this is a paid service, so don't forget to stop your notebooks, the jobs. And this is one of the jobs. I think this one is. So I have said you have an hybrid job that is executed with the Docker that is in the ACR. I know that this is kind of difficult to maybe imagine, but let's say that you have an algorithm and you have executed virtually in the cloud, and it will get you an output. And this output is here in the S3. Those are the files that have been generated. And here in the CloudWatch, as I have said, you can see all the outputs and all the maybe prints that you have put in your code to see that everything it's running okay. As I have seen, here is all the information that it will be shown in your terminal, but in the cloud. So this is one of the jobs that I have just opened. And if you want to create a good project about quantum computing, there are some pre-built templates for quantum projects that has everything that you need for a good and strong development part. That is all about the project, the installation, the tutorial, the how-to, and all the tests built in. This is the link that it's super amazing, and all the projects, all the quantum projects that I have to build, I use this pre-built template because it has everything linked, everything with the CI/CD and everything super clear. So I'm checking that everything's okay. Okay. So let's go to the real cool things, because I know that quantum could be difficult, and the development part, and the execution, and how to do this or that. But let's go to a fancy project that I really love to build. That is when you start, you are told that this is like the representation of the states, and everything looks so weird, that you have like the state in this position, that is it has an imaginary part and a real part. And for me, that I'm not, as I have said, I'm not a physicist, it was super hard to like get in and understand. So we have looked to some alternatives to this thing. So the complex number are represented in qubit state in the form of A plus BI, the real and the imaginary parts. And we have thought of fractals because there are mathematical objects that has some similarities, because they exhibit similar patterns at some scales with the spaces and times. And the good thing is that fractals has these imaginary components. So we started to think about building Julia set fractals that has that formula that is just recursive, and it has some constraints. But okay, imagine that we have these circuits and we transform it to a Julia fractal. It has these shapes, but by these shapes, we started to think that, okay, it's so cool. I will print it and put it in my wall. But I'm at the same point at the beginning. I don't understand anything about phasings and these kind of things. So we started to play with rotations. So we discovered that if you rotate a circuit with only one gate around the y-axis, for example, the air y gate, all the fractals that we got are perfectly symmetrical. So in the terms of visualization, every time we see a fractal that is perfectly symmetrical, we can know, so we can say that it has been rotated on the on the y-axis. But let's go further. If we rotate around the Z axis, for example, they are Z, the S, T, or Z gates, we have seen that in some states they have that have the positive rotation around the Z axis. They are in the equal proportion to the right with different patterns. As we can see here, that the proportion are shifted to the right. And opposite of that, if we are on the this is wrong, this is a minus. It has the other pattern, the left pattern. So with all of that, we only have to play with only one rotation more, that is the x-axis. With the RX gate, we can see the same as before, that all the patterns have been shifted on the left or the right, but in the opposite direction. The plus states are in the left in this case, and the right are for the minus ones. The thing that we discover is that the rotation around x-axis have these forms, like the first images that we have seen, not like these different axes. With that said, we started to play around with more than one gate. In this case, this is a Julia fractal representing one of the Bell states. And this is a rotation around the Z axis. And there are different images because we were testing with different mathematical equations to see if that gave us any different output. And it is unclear because we don't know if we haven't researched about what's the difference between, for example, this and this image. Because when we grow and get bigger and bigger circuits, it's more difficult to start patterns of that. And the point that we were is like, okay, if we have a block sphere and those mathematical equations, why don't you just play with them? And that's the first aim of that. As I have said, we want to discover patterns that show some information about what's happening with our states and with the rotations. Another thing that we did in this project was run big circuits and have like big images. This triptych may be posted in an art gallery in New York this year. And we also have a proposal for a children's science museum that is the same that I have shown you, but like this GIF, super cool, but with more colors and these kind of things for children. That maybe this year we can build something like that. And we are thinking about explaining all of what we have discovered in a page of the Qiskit textbook that, if you don't know it, is like one of the best textbooks about quantum computing that I have ever read, from beginners, not for not for advanced people. And let's go with the last project that I want to show you, that is the phase estimation. So here, that was one of my first research project with Qiskit and with quantum computing. That it was understanding what is the phase estimation algorithm and the quantum Fourier transform, and you can see everything in this tutorial that I want to show first. This one, yeah, this one. In this lab, you are encouraged to solve like with all the information they gave, some exercises, and you have to complete this code and this code. And here we started with this code here that is for the quantum phase estimation algorithm. And I don't want to bore you with all this information, but the thing I want you to know is that for the first execution, it was a small circuit, and the more fidelity you want, you have to add more qubits, and the more qubits you add, it start to grow exponentially. That this circuit turns to this circuit, and this circuit turns to this circuit, and so on and so forth. So it started to be like a super big problem in order to execute that in real quantum computers. So we have to find an alternative solution, that is the iterative quantum phase estimation algorithm. that we didn't discover this. This was discovered by some researcher, but we actually did an implementation using the paper. We mentioned the control if method that is a must if you want to run this, because you have to translate it in some binary thing. But the thing is that you want to work properly without that case noise and the coherence time. And this work with only 2 or 3 qubits, 2 for calculus and 1 ancillary qubit. So that gave us all the speed that we needed, and it was a super cool project and something that I'm really proud of. And the extra thing, the business thing, is Mahou doing quantum computing things? Yes, it is, and I think that all the big companies are starting to do things, and if they don't, they are actually late. But I cannot say anything about that. But I can say some things about Quantum Madrid. So go to the meetup, the Twitter of Quantum Madrid, and sign up. We have super good talks, not by me, but by really good people who knows much more than me. So if you have questions, this is the time.
Thank you so much, David. Okay, let's see. I don't know if there are any questions in the audience. Feel free to just open the microphone or type them in the chat. It's really exciting to see that Mahou is working in quantum.
Yeah, I hope that we can like share some thoughts or some algorithms, or I don't know, share something, because I really think that if big companies start to solve these things, more people will get enthusiastic about that and will start to develop and bring more people to this world.
Yeah.
Because now it's like, yeah, there are some researchers, but there is no like big companies.
Yeah. I had one question. So you have participated in several open source projects. The one about the quantum art was amazing. I didn't know anything about that one. It's really exciting to see the one. How is the experience? Not specifically in the one about art, but in general, when you are collaborating with other teams in order to create something that is going to be integrated in one of these vendors?
Yeah. So for me, I usually work in the open source world. So I just pick a project that I really like to learn or to develop. You should know that you are working for a company, because, for example, with Qiskit, everything is open source, but it's run by IBM, and there is a team behind. For me, that's not a problem. And the good thing about the open source is the people, because you can reach almost anyone that is involved in the project. In my experience, for example, I have been working in several projects about Qiskit, the Rust work, and all these things, and just go to an issue that you think that you can do it, or maybe you cannot, but you want to learn about that, and people just will help you. For example, I have been in contact with some researchers. When I did the bracket integration, I was working hand to hand with a team by IBM that gave me almost everything that I needed. And if I have some struggle or some problems, they helped me. And most of the projects that I have been able to do is because of the advocates program, because they get you in contact with a lot of people, and they have a project called camp, like it's like a camp that helps you with projects that are proposed.
That's great. Yeah, this is true. And also in the case of Qiskit specifically, for anyone here that is interested in becoming a Qiskit advocate, those contributions to Qiskit actually can be used also as a contribution, basically, towards the requirements for the Qiskit advocates. So that's one of the options that you have if you want to become one of those.
And one of the good things about that is that you can also publish with IBM if your work is good enough or your research is good enough. They will help you to publish like in a big paper. So that's another thing to have in mind.
Yeah.
Sure, they are all in my GitHub, but I can share with you. My GitHub is like here. Here I have almost everything about my projects, and the quantum related ones are like the one that I have said here, that are all like for example the Qiskit-Braket plugin, all related to Qiskit. I can later send an email or something like that you can share with them.
Yeah, absolutely. And if anyone has any questions or wants to discuss anything else, we can also put you in touch with David. So feel free to reach out. We'll see if the presentation is available. We'll have to check that. But,
Yeah, I will share with you.
Okay.
Yeah, I mean, I have a question about because I was a little bit surprised, David, when you said that you are working for like a beer company, right? And then you are really like doing this. You are really specifically working in quantum and artificial intelligence. So for me, I would never like really thought that, you know, like this type of companies would really work on that, because I would understand that the processes that they are really using, they are like much more mechanical, right? So
Yeah.
I mean, I understand you cannot really say much now, but I would be really like curious to know like what would be the benefits of such a companies to work on projects related to quantum and projects related to artificial intelligence, for instance.
Yeah. So as you have said, I have never imagined to be working here as with these technologies, but the reality is that Mahou has a big department with R&D, and there are several projects with AI. We have tons of, I don't know, every data science BI project that you can imagine has been developed in Mahou. You have to think that Mahou is more than an actual factory. It has like tons of different verticals. The core, it's the beer. Some things related to AI could be in the factory. All the machines has AI, like we have forecast about predictive analysis. When will, I don't know, a machines will broke, something like that. Those are the main things. We also have like projections with AI models about the selling, how much we will sell, to whom we should sell. Marketing is a big area when we have tons of models. In the part of the quantum thing, we are mainly with optimization algorithms, because we not only have the problem with the factory, the big factories optimizing the things. We also have a logistic business, because we have to be everywhere and we have to send everything. So problems like TSP are super important for us. And I don't know, all of the things in the mid and the long term about chemicals and different proteins will be important for us too.
Yeah, I mean, it's amazing to hear that you know, that there's like many companies really working on this and just focusing on this type of fields like quantum and artificial intelligence.
Yeah, and Spain is a good place to be right now about quantum computing because the government is pushing hard, and there are a lot of people from Spain that are starting to work in these things. And if not, you can it's bad for me to say that, but you can have a path in Europe and even the States. But I think Spain is a really good thing with even we have a Quantum Spain project, and in Coruña we will have another similar project. So I'm happy to hear that.
We have another question from Jose Miguel. So basically, what advantage do you see in working on Amazon with Qiskit over working directly with IBM's cloud and using Qiskit on IBM?
Advantages. Qiskit has tons of documentation, tutorials, videos. There is an Slack channel, a completely Slack around Qiskit. They have all these like mentorships and things. The IBM Jupyter Notebook is free. I don't know up to what time, but there is a free version. The bad thing is that Qiskit is mainly for their IBM processors that are superconducting processors. The good thing about AWS is that you have more devices. Like as we have seen, there are tons of them. The integrations will come, and it has their own SDK. But on the other hand, AWS is a payment service, and you will have to pay for everything you have you need to execute. It's also true that with IBM you have access to free quantum processors, but only the small ones. I think up to 15 qubits or something like that.
Okay, thank you. And we have another one from Adrian Martinez Rivas. So basically, if you have an idea of more or less the costs associated to using Rigetti in Amazon Web. And you mentioned also a book for beginners. So if maybe you have that reference.
We can just check for it.
Yeah.
I don't here. This is the one. No, this isn't the one. I know that there is here. It's super expensive. So Rigetti is like $0.3 per task. So each time you launch an execution, it will cost 30 cents. And each shot, like for example, if you want to run a circuit 1,000 times, one of each time will cost this amount. So you have to multiply, but execution in real hardware is expensive. So for example, a test that you are doing here could be, I don't know, 40 cents each test. So that could be expensive. And the book I talk about is the Qiskit textbook. I will this one. There is a lot of information here. Some of the algorithms I have talked about, like the Fourier transform and the phase estimation, is here. So this is a really good book. It's an interactive book. You can execute code in the book. So I think it's one of the best books. I also can recommend the Penny Lane textbook. I think it's a good book too. Maybe here. I don't know where is here. this is a really good bank of data and information. Penguin is more focused about algorithms and quantum machine learning, but I think it's a really good book. I don't know if it's called a book, but I call it a book.
Okay. Any other questions from anyone? All right. Thank you so much, David. It's been an amazing experience. Thank you so much for accepting to give a talk. I hope we can continue working. Thank you everyone for joining today. Have a nice day. This is the last one that we are having today. The next one will be tomorrow at 6, I think it is, same time as today. So see you there. Thank you. Have a nice afternoon.
Thank you. Bye.
Bye.
Thank you. Bye bye.
Bye. Thank you.
Yes, everyone. Bye-bye.